Hello, welcome to another video. I'm continuing on with the BitTorrent project, which is part of the Code Runners, not Code Runners, Codecrafters, which is, I don't know, cool little thing. It's .io, it's kind of interesting. I'm not logged in, I am logged in. But yeah, you can kind of see lots of things. Apologies for the whiteness of it. You can't actually get it without paying a bunch of money, which I potentially will, as it does seem kind of cool. But yeah, so working through the BitTorrent thing, we've got to the point that we need to basically make a hash of the info dictionary. So in the last episode, we kind of ignore all that. We kind of parsed the torrent file to get the announce key, which is the URL of where it is, and then just the length of the info hash, which we can see us doing up an info file. And we see here we get the info and we do our stuff. So what we need to do now is calculate the SHA-1 hash of this dictionary, and it's been coded. So you can't actually look at code examples unless you have finished, unless you really want to, but I won't do that. Down here there's a bunch of comments kind of talking about encoding of the byte strings, because I mean, if we look at the sample.torrent just as is, that's kind of what it is. And we see here that there's some unusual characters, most likely. And yeah, there's like a bunch of like non-printable characters, and there might even, or how do I do this? We could do that, or we could do that. No, we need to do that. Okay, so there's no like null bytes, but interesting people are talking about null bytes. But in general, it can contain null bytes, which means that you can't really use like string stuff to kind of print it, which is why when I print it, I actually convert it to an unsigned char, which is an unsigned integer of 8 bytes. What I potentially will start doing is start using like there's standard int. Sorry, I realize that this is tiny. Let's make it big. Yeah, so there is like uint 8. Where's my thing? nt. There's all of these commands. If we get, what key do we want? We want that, and do that. Something like here. Yeah, so there's like all these types that you can kind of specify which bit width you want. There's like some other things. There's like a bunch of types that we could use instead of kind of just knowing that unsigned char is actually that. But anyway, enough rambling. What the next step is actually calculating the SHA-1 hash of it, because I worked out that they don't actually want the hash done on the stuff that you print out here. They actually want the hash on more like before you get out of there, they more want the maybe this one, they want the hash of the whole info dict, which is like from here, so that D6 all the way down to that E. They want a hash of that. And how I could potentially do this is I could just do, no, I don't really want to do that, because I actually have been perusing a few different RFC type things. Well, this is a BEP. This is the BitTorrent specification, and it does talk about the where do we get the SHA-1? Not there, info hash. So it's the hash of the bin coded form, which is like the original form that we are given, what the .torrent file is. Apologies, I may sneeze, but I may have held it at bay. So yeah, we kind of want to get this hash here, and it is of the original bin coded form, because when we get the file, wherever we get the file, we decode it. We basically want to work out where in the file the info hash is and where it starts and where it ends, and then go and do some things. So down here I actually do just that. So we go from start to end, and then we print out the just whatever character, and ignore those comments for now. And if we go info something like that, here it is basically doing it prints out the first stuff, but after that 3, if we find the 3, length goes to 3. No, we get that one. So length goes to 3, and then we have a new line, and then from here we have from the D6 all the way down to that first E. So that is what we're wanting to SHA-1 sum. And how I can prove that to you, because I do like proving things, is we could comment that, comment that, comment that, comment that. And I think this should now only print the dictionary. And if I then go SHA-1 sum, we can see that it is D69, blah, 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 blah. And what it wants here is D69, something, something, and ending with 7A, 9A, 7F. Perfect. So I would say, in fact, we can even just do a, not that, get into that mode, and do that, and then do that, and boom. It is the same hash. So now, I guess what we'll uncomment all of these, because we do want them. But now what we want to do is actually work out the SHA-1 sum. Now there are some libraries, like there's this SHA-1 sum library, and there's another SHA-1 sum. But I guess this Codecrafters is in the spirit of doing it from scratch, I think. I'm not too sure. But our SHA-1 sum is actually kind of old. And if we, say, go to the start of this is the RFC for the SHA-1 sum, which was actually based off the Federal Informational Publication. No, I'm just making up stuff now. I think it might be something similar to that, but basically it was copied from this, and funnily, they actually mentioned it like 3 times in short succession. Maybe not short, twice in short succession. Anyway, what I want to do is kind of go down and kind of go over what SHA-1 sum is, because a lot of people were like scared of like doing it from scratch. Don't roll your own crypto and like blah blah blah. I just want to make a point, even though this is like saying it's like secure, and funnily it actually says like somewhere that it's like the security is based on yeah, the security of the SHA-1 assertions are made by the US government, but SHA-1 has been like known to be insecure, which like you can like look at SHA-1 some and pretend you didn't see anything there, and like if you look at just security. But yeah, you see, like you can use it as just a hash thing. But yeah, attacks is like a reasonable big thing. Oh yeah, and someone actually yeah, cool. Anyway, so show one some. It is actually reasonably easy. It boils down to 5 steps. Well, 5 kind of biggish steps, which in turn turn into like 80 operations, I think it is, from memory. But the gist is basically you're taking a message. In our case, we have a known message that we want to do. We want to take this message here, basically these bytes, and produce a hash of a certain length, which is going to be this, which is 160 bits for, 160 bits for SHA-1. So, like 32 bytes, I think that is. 160 divided by 8, 20 bytes, which we can also see by, not by, we'll just do that. It's got 40 there, but if we just go like cut minus D, that, and minus F1, get that first one, then do a WC, 40 bytes. Makes sense, I think, somehow. Math. You don't want to do it wrong when it comes to crypto. Anyhow. So, these RFCs are like kind of, they have a lot of verbosity. This is just introduction, blah, blah, blah. This is like how you define things, but it's kind of like you have hex things and you have, you basically, it boils down to you have integers and you want to do bitwise operations, so it defines what these bitwise operations are. I don't know, this just seems just like, yes, that is this, but yeah, especially like this one, it's like bitwise optical and, but you're saying that. And like the people that are reading this are probably knowing what things are. This one's kind of interesting. So x plus y, we actually define as like x plus y mod 232, which then kind of makes it still fit in a word. A word in this case is a integer of 32 bits, so it can always fit into that. We also have like a left shift operation, which we'll have to do, which, I mean, we can just do that as a define somewhere. And like it is very verbose in saying these are left shift and right shift operators. You have to pad the message. So the message has to be a multiple of like 512 bits. And the reason is because the algorithm actually takes a block of 512 bits each time. And if it doesn't have, if it's got one block that doesn't have 512 bits, it doesn't know what to do with it. So you basically have to do that. And this is kind of saying how you do padding. So you add a 1, then you add a bunch of zeros until you are 2 words away. So 64 bits is 2 words away. And then you put the length, the original length of the message, which should fit in the 2-word limit, because this algorithm's only defined for these lengths, small lengths. It's one issue with it. So then this kind of gives an example. So like this was, oh yeah, we just add 1 bit. Yeah, it's kind of interesting. You're not adding like a byte that is 1, you're adding a single bit. So that kind of makes that there. Where's the example message? This is like, then it's just like casting it back. And then you put the length at the end. That's what I wanted to see. So that 28 corresponds to that, and that 8 is just a bit right in the end, like in the 8th bit of the byte, which means it is 8. So you have to do some padding, and then when you do the padding, you can kind of fit all of these things into each 5112 bit block into 16 words, which you then call M. Now, SHA-1 has some functions, crypto stuff like have functions. Now this one is like a function ft, depends on what t is, it's only defined from 0 to 79, and it operates on b, c and d, which are defined a bit further down, and it produces 1 int as output. And so here it just kind of defines like if it's low, if it's like medium, slightly higher, and then right at the end. And you can see it does some weird things. Not once in this document does it explain why it does these things or like what makes these secure, but I guess potentially that is why things got broken easily, because someone just made up some things. And then of course you have some like magic numbers, because every crypto algorithm just has magic numbers. So here they give you 2 steps, 2 methods on how to do it. One is slightly leaner on space, but it is a bit more complex, and one is slightly leaner on complexity, so it is slightly quicker, but it may take up slightly more space. And like the difference in space is 64 32-bit words. And there's also many other ways to do this, which I mean we can see here and here, like just to close that. So what I've done is kind of taken comments of all the things I think are meaningful in this first method, because I don't know, I have a quick computer. I am not too worried about, well, actually I have a quick computer, it will get done quickly, and also I have a lot of memory. I do not really care about 64 ints. It's just not much memory in this day and age. Right, so the actual algorithm, we have like 2 buffers. We've got 2 buffers. We call the first one A, B, C, D, E, the second one H0 to H4. We also have a sequence of 80 words, which are called W0 to W79, and then a single temp buffer. And so each block we do these 80 steps, which are the first step is initialized to the H buffer to these things. The A, B, C, D are like originally set to, we already have M. Oh yeah, ignore me. Right, so we already have M, which is like our input per block. And then what we're doing is we're dividing that M, which is we each block. Yeah, so like each block will be this M. You want to then further subdivide it into 16 things, which should make sense. Which, if we go up here and see how big the block was, definition. Yeah, block. Yeah, so it's 512 bits. So the 512 bits, my math is just not great at the moment. 32, which makes sense. So we got 32-bit words, and we're dividing that into 16. I closed something. There was this like where my face is. I haven't actually got a thing where my face is to show me where my face is. So apologies if I cover it up. Right, so you divide it into 16 words. So they're going to be like your first W's. You have 80 of them, but the first 16 are those. Then for the rest of them, you work out what they are, kind of based on what lower down ones are. And this is kind of the crux on why the other method might be more space saving, because this method, using an array, you can kind of just go T-3, easy peasy, but the other one uses like a circular buffer. Could look into doing that if it is of interest, I don't know. Right, and then after you do all those W's, you basically set A, B, C, D to be the H buffer. So to start with, it will just be these. But so far, A, B, C, D hasn't been touched, and H0 blah 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 hasn't been touched. This is all just initializing the W sequence. And then you want to loop over the entire sequence and basically do all these operations, which are like pretty standard operations defined above. And then at the end, you just want to let H0 be add on what we just worked out in that whole thing. So then right at the end, after you've done the last one, the digest is that. That's all it is. And like for our thing, we'll have to then print it as hex, which that's also easy. That's not the right one there. So what I've done is I've actually kind of talked through all of this in a bunch of comments. And what I think I want to do is actually go into like make a SHA-1 sum, and maybe I'll call that SHA-1.c, and here we will like just print all of that. So that's going to be just commentary. We can remove that when we get round to it. Maybe if we go there and there and there and there. Cool. And so in this file, in fact, I was thinking, I actually want to save this as SHA-1.h. This is going to be my header. And what I'm actually going to do is get this, make it a single file header, which, I don't know, I thought it might be, how do you do it? Could be kind of interesting. So you basically have, where's just an example? I'm like, I always forget how to, this one. Maybe this one. This one's used a bunch. So what the idea is you have this header guard, which is like pretty normal, and in here that's kind of normal. So this is all just defining header stuff. That's fine and dandy. And then here it's kind of getting into implementation. So it should have like implementation. Yeah, so if we search for this bad boy, I hate modern web. Right, so we end the header guard and then we start another one. And so we're kind of just having like a header and then, yeah, we're having a header, closing off the header, and then having like the implementation. And the idea with this is I never actually have to change I never have to change my build script. All I have to do is compile main.c and that should work. So how do you do this? So you have to do header guard and like what's the standard for these? It's just like the name of your library then. Oh, they had it. Yeah, so here, what do we have? We are doing like SHA-1H, and this is going to be SHA-1H, and then here we are going to have and this is going to be SHA-1 implementation, and that's going to close off that. Something like that. And so if we like find the last one, it should be at the end. That's just like revision shit. So what we can do now is if we go to app.main. In here we can actually go something like define, well actually no, I'll kind of show you how it works. Don't go there. App.sha, this one, and maybe do app.sha. So in here we will have just our normal header stuff, and I think I just want to have a how much do I want to like abstract it? I think the user does have a need to get the message. So what we will need to have is we're going to have a this is going to be a data. How do we do it in C? Unsigned char star. Now this is when I kind of want to just go int not that t and like find the d and do that. So this is going to be our data, and then we're going to have like a size t length, and I think I might want to do something like this just to make it clear what the things are. And in this we're probably going to return a thing, and I think that might be it. So that's going to be our digest, I guess. So other methods are, in fact, this RFC even gives an example C file that does it, but I don't know. This kind of has like you do like a reset and input a result, and I kind of want to just wrap that all into one, because as a user of the API, all I really want is to get the result. And so this int is going to be like the result, whether it failed or passed, and we're probably going to have to define SHA-1 length, and what is the SHA-1 length? I think it even has it in here. If we do a length, if we do an underscore length, no, if we just do a C code, this one in the header, there is a hash size. That's a context. Yeah, where's this guy? It is just 20. So that is going to be 20. And does that make sense? It was 160 bits. It was 160 bits. So if we have 20 bytes, we have 160 bits. So yeah, that is something like that. Cool. And so the idea is, I kind of want to put that just in there. Yeah. So the idea is, if we kind of go main back to here, we can go include SHA-1.h. That is what we called it, and where do we? Yeah, so here we probably just want to do. We want to make the digest, so we're going to have unit 8t digest, and what we'll call it info. We'll call it info hash even, and this is going to be SHA-1 byte length, and then we're going to do SHA-1. Is it just that? Apologies, I started off badly in the day. So if we open up SHA-1 digest, SHA-1 digest, and what do we want to send in here? We want to kind of convert this uint 8. In fact, I think I want to do something like const here. Const the data is going to be info start. The length is going to be info end minus info start, which should be, we can double check that in the thing. In fact, that's the first thing. Right, so then the result is just going to be info hash, and probably needs to be a pointer to it, and instead of doing that, I what do I want to do? I want to go here, I just want to go here, and I think I just want to go if not. Something like that, and maybe one more. So if not, then do this. Old C not having rules, but we can actually have rules because we can do a cheeky include to std ints. Cool. So if we couldn't get it, then I don't know what to do. We just go to end, I guess, and that's what we want because it defaults to data error, and if we couldn't get the hash, that is or I don't know. What is I feel like that if it fails, it's probably going to be a data error. Otherwise, we could set. Yeah, in fact, we could just set ret. Ret equals that, and if ret not equal to 0, do this. I kind of want this to be SHA-1 ret. Oh, lots of spaces. SHA-1 ret, and then ret can be SHA-1. Something like that. Cool. So in here we can probably just go to here and get rid of that. If the hash did succeed, then we want to print it. So for we can just do I equals 0, I is this then SHA 1 byte length, and I plus plus. And in this, we just need to just do a printf percent x. Now, what output did it actually want? It wanted lowercase, and here we can go info hash, and here we can just go I, and I kind of want get that. Cool, so that is going to print that. Otherwise, we also need to go info hash, do that, and then print f line. Right, so ideally that is going to print out what we want. Now the problem is, keep on closing this shell. The problem is that if we run it, it doesn't know a few things. So I guess what I could do is do this. I might just do some things. Right, so it doesn't like this. How do we do this? Do we do that? I think it might be that. It doesn't like that. We can just pass it. How does this thing do it? I mean, I'm copying somewhat off this, but final. Result, was it? Yeah. That's kind of weird because it kind of seems like it might be passing by value a bit, like C arrays don't do that. I need to get used to C again. Right, so now we have like a linking error actually. So it's like undefined reference to show and digest. And how we can do this is, well, I guess we also need to, I think I need to BD that and buff char. BD that and buff char. And what do I have in my buffers? I've got a lot of stuff. BD 14, 17, 14, 17, BD 14. And do that one as well. Cool. So what we can do here is if we grab this, we can actually define it down here. And if we do this, we can probably grab this. So that's just going to be how we do it. And no. So what we can do here is like, I don't know, we could probably just do like a printf here, just to show that it is working. Prints here. That's kind of cool. That it's wrong though, because this should be if def. Is that how we do it? Yeah, if def. But this. Come on. Modern web. Like, how do I search things? Yeah, so that's if not def, but then we also want to define it. Did we do it? Yeah. Cool. So now it should get that old, what do we have? Yeah, we've got that. We've got this, that seems not right. Yeah, we didn't want that. Well, actually, we can look at the driver. They had a example testing, which is something I potentially might do as just a test. But yeah, we do our things, we reset it, we do our thing, we do a bunch of inputs for like all of the things. See, like all of that stuff just seems like it could be done. Then we do that and we just pass in that. Now what is that? That is, yeah, cool. So yeah, I have once again confirmed to myself that I don't need to do anything. Right, so now what does it do? It only has a linker error. So how you get this solved is you do define SHA-1 implementation, and then it works. Just works. But of course, we need to actually do the thing. So how I kind of imagine doing this is just stepping along and doing all the steps. Has been reasonably long. I'm wondering whether to break this up into 2 episodes or just jump into it really, because I've got all the boilerplate, and like I think we need to just return 0, and then yeah, if we return 0, it like gives a little hash. And what we can do is, that'll just be random data. Won't be random data. Well, it's like random in a sense because it's like uninitialized, so don't know what it's gonna be. Don't know what it's gonna be. I think you can initialize it to all 0, but we'll start doing things a bit different. So what I'm kind of want to do is we do have to do this what do I mean? I kind of like the idea of copying around a context like they do in this one, because the context is storing the intermediate hash, which is, I guess, kind of important because you need to know the intermediate hash. And where do they even define the context? This thing, which like you have to like pass into it. Yeah, so gosh, alright. Divided by 4. So this is like the message block. I read through this all last night. Haven't quite got it. Yeah. So this is getting the result. If we haven't computed it, we pad it. How does the driver fire this thing? It's kind of weird. I mean, even so it resets it. Alright, so what do we do once we reset it? We repeat count J. Like, what is this magic? This is just magicness. Like, this is the test. Real easy to read. Right, so we do up to 4. So we're doing 4 things. Is that because we have 4 tests? Yes, it is. Like, I probably would have done the size of this. You have to do like a size of test array divided by size of test array 0, because otherwise the size of this is just actually a pointer. It's just what it is, and to get that number you need to kind of get this and get that. It's just how it is. Right, so we do the test. This is, what's this repeat count? Repeat count is, we do a lot of repeats in that test 3 for some reason. So normally we just do 1. Cool. We input the test array, and it's just going to be the length of the test array. So that's kind of what we would have in the SHA context, is just there, past that, and then at the end of this, which is the repeat count, we just get the result, and then we print it. We should also do that. Cool. Sharp 1 digest thing. That's what we want. Future proofing. Cool. So so if we just have a bunch of 3s, it reckons it might do this. I'm just trying to understand this. How do we do this? We just do like a times, or whatever this number is. No, we have to do like a minus c. Yeah, so that's kind of what we want. It puts in a new line, so we just want that. We can do a quick that. It does have 1,000 characters, and so if we just do SHA-1 sum of this, it gets 34AA97. Yeah, that looks right. It's weird how they don't. Weird. Like test cases should be straightforward, so a person reading it can understand what the test is testing. This is like adding weird logic to how you generate your test cases. Like it yeah, I don't know. But yeah, so we are only really passing input once, but we could potentially pass it multiple times. But really, it shouldn't need to. Right, so this is probably the input. That's the, yeah. So we do the input. If it is computed, yep, that is probably right. So here we are like copying. Yeah, we're copying the message itself into our message block. and so the length, it's kind of weird. Like I don't know. Yeah, like why is that not tabbed out? It's bizarre. Like this matches up with this, but like none of this is indented. It should just be it. But yeah, it's kind of weird that they don't just test the length before doing this loop. They kind of keep on adding it, and then if it gets too long, then they'll like bail out. It's kind of interesting. And then if we get to the last one, we process it. So yeah, every 64th one we will process it. That kind of makes sense. So yes, what I think we need to do is maybe go back here. So yeah, ignoring all of that, we need to have like some sort of a structure to. Well, we kind of just need to have a you and 8 t. We want that, and how big did they have that? That was like 64. Where is our context? Um, 64. So partly I'll like copy from the code, but I kind of do want to understand what it's doing. So here we're going to have like a message. Well, we're going to call it a block, and it can be 64. And here we will probably just want to do like while like they do like while length is positive, because yeah, the length minus will test the one, but then if it is 0, that will bail out. I'll just have to check. I kind of want to just do for an IDX equal 0, IDX is less than length. Potentially we can just call this a size t, and IDX plus plus, and if IDX is divisible by 64, then we will do something, but that will be at the end. Hold fire. Yeah. So I think this I will actually have a leave and come back to, just because it's starting to get into the kind of bits and pieces of it. Spend an hour going, getting the boilerplate and talking through it all, but it's just how it is. I may even stick the videos together, because that might be better, but I think I just need a little break, come back to it. So that's that. Thank you for watching. If you enjoyed the video, feel free to watch some others. I make a few videos. and let me know what you think. So yeah, have a great day.